That's the key point of this, okay? But I would have to solve, this represents coupled equations, because M ranges over all possible values from minus infinity to plus infinity in principle. Okay, so I turned it into coupled equations, which isn't computationally such a huge gain, okay? So no, to be honest, I won't say it that way. We've solved this equation once, okay? Oh, the normalization of the wave function is easy. I mean, this is normalized, right? So this is, yeah, I mean, that's the only normalization we require, that is required, okay? So this sum has to be normalized in the same way, okay? Now, we can do one more step, and that is to define, we can define a new function, phi m is e to the I omega t psi m, and we're always free to do that, right? I've just defined a new, I mean, these things are time-dependent functions. I've just defined a new time-dependent function. I can always do that, and if I substitute that in there, what we'll find is we get rid of these factors too, but otherwise the equation is just an equation for phi. I'll show that one in a minute, okay? So the real point here, we're going to use this for interpretation, yeah?
So what's the physics of this phi m? Because for given...
of this one?
Yes.
I'll get to that one in a minute.
Spaces, so how can you achieve?
Say it again. Okay, that one.
I mean, for given force, the base phi is fixed.
Ah, but
So
here,
how can you understand this phi m in this case?
okay, I'll answer most of your question on the later slides. Part of your question I'll answer now. This equation for the psi m's, or psi n's, doesn't have a phi in it. All it has is the pulse envelope, and of course the frequency, right? So I solved this equation once, and I can construct all the pulses that have this envelope and this frequency for any CE phase. Okay, that's what this relation allows me to do. I solved this equation once, given a pulse and a frequency. I can construct all solutions for all CE phases of that pulse here. Okay? Yeah?
So the very last equation, that's basically going into the direction picture.
Oh, this one?
Yeah.
No, it's kind of the opposite. You're coming from the interaction picture. Let me advance. I'll show you the equation. I'll make it easier to say. So that top equation is the equation for phi. Okay? And oh, I messed up. There should be an n in here. I forgot the n, or the m in this case. I m omega t. Okay? But it's like going to the interaction representation, except we're going the opposite direction, right? Because in that equation, we just had h naught psi m. In this one, we get h naught minus n omega. So, in a sense, this is the energy of the photons. Okay? So we're putting it back in. Going to the interaction representation, we normally take that away.
Okay, then, sorry.
Go ahead.
If you look at the second equation, that you see that's some kind of,
This one?
yeah, some kind of interaction picture in terms of the phase theta time.
Well, this equation still depends on time. So it's not instead of time.
Right. So the second equation would be you go into the interaction picture in terms of the phase. You got to say transformation.
Well, but I mean, there's in terms of the phase.
So it's not a normal interaction picture, but
There is a connection there. I'm not sure that's it.
Okay.
And another question?
Back to my previous one. So,
Okay.
do you have a classical equation for the photons? I mean,
Here, the electric field is given here. It's fixed. Okay, and so it's purely classical. It does solve the Maxwell's equations, but it doesn't know about the atom or molecule at all. So it's unchanged. Okay, if you want to think about it that way. So it's not like what Ken was telling you about the coupled system. This would be completely uncoupled. The laser field is given. We don't follow what happens to the light at all. Okay. You you couldn't be so large.
So it's more general comment also in relation to this lecture.
Yeah.
So maybe, I don't know, if you find that it would be helpful just to mention Floquet theory and Bloch theorem. It's kind of related to this idea about using the periodicity.
True.
Maybe
So,
some students know about that.
It raises the question about the Floquet theorem, and to be honest, I purposely left it out because in a sense it confuses the issue, because this is not Floquet.
No, but it's still the Fourier decomposition is...
True. Let me say it this way. In my next lecture, I'll tell you about Floquet. Okay? I want to separate the concepts in time so they don't confuse you. But it's true. So think of that as the sort of forewarning that we will talk about Floquet, which is a similar idea but different. Okay? This is not Floquet. What I've shown you so far, this equation is exact. No approximations, right?
So
Yeah.
for Floquet, you assume that your field is constant. I mean, it doesn't have an envelope. And
That's right. That's right.
do you assume like an envelope here, or?
In what I'm doing?
Yeah.
Absolutely. That's what E naught of t is. That's the envelope function. So this works for pulses exactly. There's no approximation.
Okay, but can you extend Floquet to this case when you have an envelope, or just for constant driving?
There are various extensions of Floquet to having an envelope. But they, again, they're related, but they look slightly different than this. Okay. Yeah.
Before that, the Hamiltonian is periodic and the results should be yes. And then because of the linearity independence, you omit it. And the final equation it does not depend on phi. And what is it? The problem is periodic in phase, and you are looking on CP effects, and the equation does not depend on phase.
But that's the beauty of it. It doesn't depend on phase. So if I solve this one, I can get all C phase dependence exactly with this equation. Once I know the size, I have all the C phase dependence. Right? That's the beauty of it, in my mind. Okay? Otherwise, I have to solve this equation for a bunch of different phi's.
I could add that this is exactly the same problem, except you replace t by x as diffraction by periodic potential. So you get the Raman-Nast solutions, right?
Sure.
Yeah.
Sure. And then, again, just since Floquet and these other sort of issues were brought up, I'll point out Floquet uses the periodicity in time. I'm using the periodicity in the phase. Okay? One key difference. For the phase, there is no derivative in here. For the time, there is a derivative. So that's it's a mathematical distinction, but an important one. Okay? For periodicity in phi, I don't need the Floquet theorem. But like I say, the rest of it follows exactly. Now, because of this equation, and by the way, I will point out that if there is no envelope, this is the Floquet equation. If E naught is constant in time, this is the Floquet equation. And there's one way that we can make the connection that omega is really, or n, is really the number of photons. Okay? There's one way that we can make the interpretation that psi n or phi n is an n-photon amplitude. Okay? Was there another question back there? Okay, there's one up here. Yeah.
You're saying that your top equation there is exact,
Yes.
but you're also saying that you're not accounting for the changes in the field that arise when electrons are freed.
Oh no, I mean electrons can be free. That's not the problem. What's not accounted for is the change in the field, the light field. Okay.
Oh, you mean you're not accounting for the fact that you're losing the photons?
Right.
Okay.
Or that I'm generating new frequencies.
Yeah.
Yeah. That part is not accounted for. That's what he was asking about. Was am I following the photons? No, I'm not following the photons dynamically. Okay. And so this is just bullet points basically repeating what I've said, is that this is an exact statement. These amplitudes don't themselves depend on the CE phase, which means the CE phase dependence is analytic and explicit. Okay? Moreover, this applies to any system. I didn't tell you what H naught was up here. I didn't tell you what the dipole was. So this is any system. And by the way, I wrote it in length gauge for those of you who know what that means. but it applies equally well to velocity gauge. Okay? So as long as you're working in the dipole approximation, this is fine. But as you guys know, you've taken quantum mechanics. Once you have the wave function, you have everything, right? Well, if the C phase dependence is explicit, I have the wave function explicitly in terms of the C phase. That means I can derive all the C phase dependence I want, because I have the wave function. And that's what we'll do. We'll use this to derive general results to tell us about the C phase dependence. So for example, and this comes back to Tony's comment, what we measure experimentally is the momentum. So in the P plus H problem, if you take the relative momentum between the P and the H, then we're measuring that momentum direction. Okay? So we're taking the differential measurement of probability with respect to the momentum, the whole momentum vector, and you calculate that by taking our time-dependent wave function, projecting onto this scattering state that asymptotically is going out in one direction. Okay? Just substitute in our expression for the time-dependent wave function and expand it out. Okay? Very simple. So you see then that C phase dependence, in other words, all the C phase dependence is right here, remember? So for there to be C phase dependence, n and n primes should not be the same, they should be different. And if n is the number of photons, that means different photon amplitudes have to interfere. More than that, these are the amplitudes. These matrix elements are the amplitudes. Okay? And so for them to interfere, they have to contribute to the same direction, they have to have the same K. And if they have the same K, they can interfere. Okay? So this is exactly the coherent control, Brumer-Shapiro, I don't know, two-pathway interference, Young's double slit, however you want to explain it. Okay? That's exactly what this is. So C-phase effects are really coherent control. Okay? Everybody good on this page? Because the rest of it is going to really use this idea. Yeah?
So for instance, something that was said a couple of times yesterday, which is no C phase effects in one photon processes.
Right.
Right. So how do I see that from this expression?
Well, in that case, the only amplitude here that would be non-zero would be psi 1. Okay? And probably you presumably would have psi 0 left over because you don't get rid of the whole ground state. Okay? But if you look at, but psi 0 will just be a bound state typically. So let's say you start in a bound state, that will be 0 photons, 1 photon ionization, you get up to the continuum. Okay? And so the only thing with the direction here that's in the continuum will be psi 1. And so that would be 1 minus 1, no C phase dependence. And all the other terms are 0. Yeah?
The simpler way of saying it is that for a one proton process, you have an amplitude and its complex conjugate, so the phase goes away.
Okay.
If you only have...
I mean, that's true, but I'm not sure that in here that I see that as easy.
Well, n equals n prime.
Right. That's what I said, I think. Okay. Okay. Okay.
So it's really the off-diagonal
Absolutely.
entries.
Right. It's different photon pathways interfering with a caveat. Yeah, that's right. Different photon pathways. Because n has to be different than n prime to have any C phase effect left. Because if n equals n prime, this just reduces to 1. Yeah. Yeah.
But the person on that, you somehow see the CP effect.
Let me get to that in a minute. Other questions?
So then I would say that if I have an unlocked laser,
Yeah.
right, where phi is now a random variable shot to shot,
Right.
I integrate over phi.
Absolutely.
All the diagonal terms go away, and that's where the C phase
Yes.
was.
And that's trivial to see when you have this expression. Yeah. So did everybody get that? Because sometimes when people do experiments, they don't control the C phase, and the C phase may change randomly from one pulse to the next. So the measurements are really a random distribution of C phases. So how would you get the answer? Well, this is the observable, right? That's what you compare with the experiment. You compare the observable. And so if you want a random distribution, say the uniform distribution of C phases, just average this over C phase, which means everything with n not equal to n prime goes away. So only the pieces with n equals n prime will survive. Okay? And again, that's one advantage in my mind of having an expression where these things are explicit, because you can do all those manipulations without solving any TDSE. Okay?
Can I ask one more question?
Yes?
So if you've done it, because I agree, computationally, this is not the way to go. I mean, because, for instance, if you imagine solving for 20 different CE phases, you could do that on 20 processors all at once.
Sure.
Whereas coupling 20 orders, right?
Doesn't scale the way. Yeah.
Okay, but this is still, let's say this is extremely useful. If you have the solution, like it's more if you've tried this,
Right.
if you now do the solution on 20 processors, get the answer for 20 different CE phases, can you unfold these?
Absolutely.
And have you tried that?
Yeah, we've done that.
That works.
So basically what you're saying is, we want that information. We can either solve this equation, or we can solve the original equation for this guy, and then use this relation to get the psi-ns. All you have to do is a Fourier transform in CE phase. And absolutely, we've done that. It works beautifully.
So then there's the whole Nyquist sampling and all that.
Absolutely. Actually, I wouldn't even worry about Nyquist sampling, because for the most part, we can get everything with 4 CE phase points. Because of aliasing and energy separation, we can separate all the different photons that way. I can tell you more detail what I mean by that later if you want. But yeah, I was going to mention that a little later, but this is a good point. This is a relation that goes both ways. It's exact. So if I have either one of them, I can get the other. Okay? And so if you want to learn about photon pathways, and by the way, this is a way to define a photon amplitude, which may not otherwise be such a clear thing to define. This is a way to define it. Okay? Moreover, this is a relation that holds it every time. That means even during the pulse it holds. So we can follow the photon amplitudes during the pulse and see how the 1 photon, 2 photon, 3 photon things get populated during the pulse. So it's an interesting way to follow the dynamics. However, one caution, during the pulse, your answer will be gauge dependent. Okay? You can define this is a perfect way to define it, but just be aware that during the pulse, everything, all of these things go away. They aren't gauge independent. Okay? But, as many people have already plotted things like ionization probability as a function of time during the pulse, which is not gauge independent either, this is an equally good thing to look at. Okay? Now, okay, so we have interference of these amplitudes. Let's look at a common observable, which is the CE phase-induced spatial asymmetry, which means that you just take whatever goes up minus whatever goes down at a given energy. Okay? Now, if you use the expression for the momentum distribution that I gave before, then you can simplify it to this kind of an answer. Okay? Sum over n even and n prime odd, and this E superscript and O superscript means even and odd parity. Okay? Even and odd parity. So what is this saying? This says that to see any CE phase dependence in the asymmetry, you need n different than n prime, but that's guaranteed because one's even and one's odd. But you also need an even parity state to contribute at a particular direction, and an odd parity state to contribute in the same direction. We already saw that example though. Okay? When you have dissociation or ionization, because remember, I'm giving molecular examples, but there's no specific system specified here. So everything I'm saying applies to ionization, dissociation, dissociative ionization, everything. Okay? Ionized DNA if you want. This will give you the answer. Okay? And that's the power of it. I don't solve it this way. I don't solve these equations, but I use it to guide my thinking. I use it to interpret. I use it to predict. Okay? But you'll also notice that the lowest order CE phase effect is when n and n prime differ by 1. Okay? So you'll get an e to the I phi. That would be like if 1 photon and 2 photon interfere. That would give you e to the I phi. Okay?
Brett, I have a quick question.
Yeah.
Before that. So, you wrote your field is a standard short pulse field
Yep.
there, and then for most fields, you don't have omega and 2 omega contained within that pulse.
You don't need it.
So, but then when you go to this picture, right, you show omega and 2 omega.
Sure, but n and n prime can differ by 3. and 4. And so I'll show you, let me show you the picture and you'll see what I'm talking about. Okay? So the next picture, I think, addresses this question and an earlier question. And that is, how do we understand these C phase effects maybe in an energy picture? Because again, we're using photons, so we're implicitly in a frequency or energy domain sort of picture. So what I'm sketching here is energy here. This line would represent, for instance, the energy of the ground state. If you're sitting in the ground state and you absorb 1 photon, that's 1 arrow, 2 photons, 3 photons. 3 photons get you into the continuum because you're above 0 energy here, you're above threshold. And the peak that you would get in an ATI spectrum or something like that might look like this. Okay? Centered on the 3 photon energy with some width. But you would also get another one at 4 photons, another one at 5, another one at 6, and so on. Okay? Now 3 photons would put you in an odd parity state if you start in an even parity state. So 4 photons is even parity, odd parity, even parity. That's what the colors of these are supposed to remind you of. Okay? And remember, for spatial asymmetry, you need even parity to interfere with odd parity. Okay? Well, do we have any interference of even parity and odd parity here? What do you think? Who says yes? Who says no? Okay, again, most of you aren't voting. That's not an option. Okay? If they interfere, remember they have to have the same final momentum. That means they have to have the same final energy. And this is an energy axis. So for this odd parity to have the same energy as the even parity, we have to look there where they overlap, right? And yeah, there's a tiny little overlap there, but it's tiny. So in principle, yes, there's interference. In practice, it's really, really tiny. Okay? So I would give partial credit for both answers. Okay? So interference is possible only when these overlap. Now what I didn't say is the width of this peak is related to the bandwidth of the laser pulse. Okay, let's stick with transform limited for a second. Okay? For transform limited laser pulses, the width of these individual peaks are related to the bandwidth of the laser pulse. So to get them to overlap, clearly you need broader energy distributions. Okay? And how do you get a broader energy distribution? Shorter pulse, because you need a bigger bandwidth. Okay? So this leads to the conclusion that most people expect, is that interference is possible only when those overlap, which means short pulses. Okay? And of course the interference now is in these gray regions. But notice it's always in the exponential tail. It's always in the tail of this power spectrum. Okay? So for this reason, at least and this picture is sort of the approach from low intensities. This is sort of a lowest order perturbation theory kind of picture. Coming from that direction, you would expect C phase effects to always be small because they're always in the overlap of the tails. Okay? If you get to high enough intensity, these things start shifting around and really broadening and going crazy. The picture still holds, it's just not as easy to predict. And you can have larger C phase effects now. But we can also predict that if we were to look at the C phase dependence, you would only have terms like cosine and sine phi, cosine 3 phi, sine 3 phi. You would have the whole trigonometric series with odd frequencies. Okay? Now, if I take a survey of the C phase results that were available in March of 2014 anyway, so these are experiments. Okay? And I'll tell you without going through these in detail that all of these show exactly this cosine phi phase dependence. Okay? That would be the period. So here's a phase axis from 0 to 4 pi. So 0 to 2 pi. 2 pi is the period. That's just cosine or sine, right? If the period of this asymmetry, which is plotted here, is 2 pi, that's just cosine phi or sine phi. And my contention is that that's a trivial consequence. The cosine phi and sine phi is a trivial consequence. And I point that out because there are a number of theories, a number of models that claim that getting this cosine phi and sine phi agreement is a really good thing. I would contend that you can't help but get that if you mix even parity and odd parity. You have to get that. There's no choice. So getting the right periodicity says nothing about your model except that you mix two parities. Okay? If you really want to test it, what you need to get right, is the magnitude and phase of the C phase dependence. Okay? What does that mean? That means getting these guys right. Okay? Now, I'm running out of time, so let me go through this a little bit quicker. We've done it once, so it should be a little bit quicker. We can go through the same analysis for the yield, which relates to some of what Ken talked about and what he asked. So if we want to look at the yield and modulating the yield with C phase, you can do exactly the same analysis. You get this sort of equation. The difference now is that n and n prime are any numbers, but these amplitudes, you have to have contributions from even parity at the same place as even parity, and odd parity at the same place as odd parity. Okay? So this is interference of even parity with itself and odd parity with itself. It's not even with odd like it was for the spatial asymmetry. But to get C phase dependence, you need n to be different from n prime. So how does even parity interfere with itself? What's the minimum number of photons for that to happen? Well, 0 is the minimum number, but that gives you no C phase dependence. So 2, exactly, 2 is the minimum number to get C phase dependence. Okay? And so you expect, so here's the same kind of picture, schematic picture for the effect. You have narrow pulses, broad pulses. So that would be the spatial asymmetry between odd and even parity. Yield dependence of C phase is down here where odd parity interferes with odd parity. That's down there. Or even parity with even parity. That's down there. So it's even smaller. It's even further out in the tails of the power spectrum. Okay? But if you have it, it's going to have periods in a Fourier series that are the even frequencies. Okay? And again, survey of experiments showing yield C phase dependent yields. And what you'll see, this is a range of, in this case, 2 pi. And so you have 2 periods there. That's exactly the cosine 2 phi kind of dependence. Okay? And all of these are consistent with that expression. Now, that raises, so we have a picture. We've explained things. Now let's try to predict things. Okay? So what else can we predict? One big question, or one question that came to us at least, was, do C phase effects depend on the pulse length or the bandwidth? Okay? Most of the people arguing from the field picture would argue it's the pulse length, because you need the peak field to be very different. Okay? But from our picture, we're in energy domain, right? We said it's the overlap of the power spectrum. In that case, pulse length has nothing to do with this. We need to know about we need a broad power spectrum, but that's the bandwidth. Okay? So if it's just the bandwidth, that means we should be able to see C phase effects even for long pulses, as long as they have a broad bandwidth. Okay? How do you get a long pulse with a broad bandwidth? Anybody? You chirp it, right? Because once you add chirp, the relation between bandwidth and pulse length gets relaxed at least. Okay? So we can do the calculation. So here's our dissociation of H2 plus again into a proton plus hydrogen atom as a function. So this is the KER spectrum, the energy spectrum. And along this axis is pulse length. Okay? The middle panel shows you what happens if you take just a transform limited pulse and look at C phase effects. So this is the spatial asymmetry for a C phase of 0. Okay? So you can see the spatial asymmetry normalized goes from -0.4 to 0.4. So you see spatial asymmetry in this particular case out to about a pulse length of say 20 femtoseconds. Okay? But if you positively chirp the pulse, but keep the bandwidth equal to a 5 femtosecond transform limited pulse, then you can see C phase effects all the way out to 60 femtoseconds. Okay? And if you negatively chirp them, you can also see C phase effects out to 60 femtoseconds. Okay? And for, this is 800 nanometer light, so 60 femtoseconds is how many cycles? Well, 2.5 femtoseconds per cycle.